So, welcome back to SJP Math. So, today we'll be looking at a new quite algebraic topic today. So, it's Vieta's formula. And this is one of the most important concepts in math and is usually not taught in high school maths, but in Olympiad math and competition math, this is one of the most important theorems there. So yeah, basically Vieta's formulas, if I want to describe it, is it's a relation. It's something that gives a relationship between the coefficients of a polynomial with its roots, and it becomes really useful in that way because without even knowing the roots, you can find relationships between the roots and get a lot of information from those equations. So yeah, so this formula works for any degree any polynomial, so like of any degree. But first we're gonna start with degree 2 polynomials, so quadratics. So let's say we have a quadratic ax squared plus bx plus c, and let's say it has roots r1 and r2. Okay. Then by Vieta's formula, we have that the sum of the roots, I'll maybe put that in a different color. Then the sum of the roots, r1 plus r2, is equal to negative b over a. And the product of the roots, r1 times r2, is equal to c over a. So these two look pretty similar, but except that there is a negative stuck here, and here is the coefficient of x on the numerator and the constant in the numerator here. That looks like a D, but that's an A. So it looks pretty interesting, I guess. So let's try to look at some quadratics to see if this actually works. So for example, let's say x squared plus 5x plus 6. And the roots of this quadratic is negative 3. That 3 doesn't look that good. Negative 3 and negative 2. So if we take the sum of these two roots, we get negative 5. And we can certainly see that negative 5 is equal to the negative value of 5 over 1. So yeah, we can certainly see that the negative value of b over a, so negative value of 5 over 1, which is negative 5, is definitely the sum of the roots of this quadratic. So yeah, we have verified this equation. And what about the product of the roots, though? So the product of negative 3 and negative 2 is equal to 6. And this is indeed the value of c over a in this quadratic. So 6 over 1, which is 6. So therefore, we can see that, curly brackets. So definitely we can see that this formula works for this quadratic. So yeah. And this was a pretty simple example because the leading coefficient was not equal to 1. And what was equal to 1. So so this a part became a 1, so it was just negative b and c for these cases. Yeah. So that is Vieta's formula for a quadratic, and it's pretty straightforward, I guess. Actually, let's try another example to get the hang of this. So let's say we have 2x squared plus 5x plus 2, and we know its roots are negative 2 and negative half. If you factor in and stuff. But then let's say we don't know what these roots are. Then the sum of these two roots, let's say r1 and r2, by Vieta's formulas, we get that it's equal to the negative of 5 over 2, so it's equal to negative 5 over 2. And we can check that this is true because negative 2 plus negative half is equal to negative 5 over 2. And the product of the roots by Vieta's formula, it should be 2 over 2, which is 1. And indeed, negative 2 times negative half is equal to 1. So yeah. Yeah, that's how Vieta's formula works on the quadratic. But yeah, this is the most common case. But we should look at the general case to see if how this applies to higher degree polynomials or just polynomials of any degree. So let's get our next box. So generalization of the Vieta's formula. So let's say we have a polynomial an times x to the n plus an minus 1 times x to the n minus 1 plus all the way up to a1x plus a0. And let's say it has roots. It has roots r1, r2, all the way up to rn. And yeah, if you're not familiar, degree n polynomials have exactly n roots, but I guess it can be also be said that at most n roots, because some roots may be repeated, but that will be discussed in another video. And so if this polynomial of degree n has roots r1, r2, all the way up to rn, then here comes the complex formula. So we're going to have our sigma I doesn't look. Wait a second. I2, I2 all the way up to IK. I'll just write this out first and then explain it to you guys, because this equation is pretty long. R82 or IK. Oops, that bracket. Negative 1 to the power of k times an minus k over an. Okay, that was a pretty long equation. So if you look here, this means that Ri1. So if you take the product of every k elements of the set of roots, and then add them all together, then that will be equal to negative 1 to the power of k times an minus k over an. Yeah. And yeah, the formula looks really complicated, but then it turns out that it's pretty simple. And if you just understand the concept behind this, it'll be easy to understand how this applies. So yeah, to get a better understanding of this, let's look at when k, for any k that is between 0 and n. So yeah, for any k, this applies. So if you take any k elements from the set of roots, you'll get, and then add them all together, you'll get negative 1 to the k times an minus k over an. Yeah. So where I1, I2, and IK are all between 1 and n. So just any k elements. So yeah, let's look at degree 3 polynomials actually, because after this, degree 3 polynomials are the most commonly used Vieta formulas in Olympiad math. So yeah, let's take a look at that. Okay, so let's say we have a cubic. So yeah, degree 3 polynomials are called cubics. So ax cubed plus bx squared plus cx plus d. Okay, and then let's just write everything else in blue, because I like using colors. I should have put this in blue, but it's a general case, so it doesn't matter. So let's say this has roots r1, r2, and r3. Yeah, pretty straightforward. And let's take the sum of them. Then in this case, k is equal to 1 because here we're taking the product of every k elements from the set of roots and then adding them all together. But here we're adding these individually, which means that k is equal to 1. We're taking one element from the set of roots and then adding them all together. We're adding them individually, so here k is equal to 1. So using this formula, this is equal to negative 1 to the power 1, so just negative 1, times an minus k over an. And k is equal to 1, so an minus 1 over an. And negative 1 is just negative, and then an minus 1 is equal to b, and an is equal to a. So we get that the sum of these roots is equal to negative b over a. But here in the quadratic, we see that the sum of the roots is equal to negative b over a as well. So we're kind of starting to see a similar thing happening on both things. Okay, so let's try another case. So this time when k equals 2, so when we take every two elements from the set of roots and then multiply them together and then add them together. The product of every two elements in the set of roots and then adding them all together. So basically the pairwise products, the sum of the pairwise products. Oh, that 2 looks too big. R1 times R3. And this is equal to, so here, as I said before, k is equal to 2 here, because you're taking every two elements from the set of roots. So negative 1 to the power of 2. Well, negative 1 to the power of 2, since 2 is even, negative 1 to the power of 2 is just going to be 1. We'll just not write it there. And then it'll be so it'll just be an minus 2 over an. And an minus 2 is equal to c here, and an is equal to a. So we get that the sum of the pairwise products of R1, R2, and R3 is equal to c over a. And again, we see a similarity in our equations. But then again, we have one more case because k can be between 0 and n. And here n is equal to 3 because it has degree 3. So we can look at when k equals 3 then. So R1 times R2 times R3. Taking 3 elements from the set of roots and multiplying them all together and adding them. But then we only have 3 roots, so then it will just be the product of all of them. So this will be equal to negative 1 to the power of 3. And since 3 is odd, that will just be equal to negative 1. So negative 1 times an minus 3 minus over an. And yeah, negative 1 just makes a negative, and an minus 3 is equal to d in this case. And an is equal to a. So yeah, so the product of the roots of a cubic is equal to negative of the constant over the leading coefficients. So yeah, we can clearly see a correlation, no, not a correlation, but like a similarity between these two. And what we notice is that every time as k increases 1 by 1, we take the coefficients that we look at for the numerator takes a rightward step along the polynomial. So when k equals 1, it's here, and then when k equals 2, it's c. We're looking at c, and when k equals 3, we're looking at d. So we keep moving along the polynomial. Like, it's pretty easy to understand it that way, and we just divide by a then. And we can also see that the negative sign, the sign of the fraction keeps alternating, and that's because as I was saying as I was solving this, negative 1 to the power of an even number will give 1, and negative 1 to the power of an odd number will give negative 1. So that's why the signs keep alternating. So for odds it will be negative, and for evens it will be positive. So yeah, so this formula looks really scary, but then if you just put it for a specific degree polynomial, then it's pretty easy to understand what this actually implies. Yeah. So actually, I probably might not try an example because this is pretty straightforward. So, because in this video we discussed what Vieta's formulas are, But in the next video, we're gonna look at how we can actually use these usefully. We can effectively use these formulas in math problems to easily solve them. So yeah, make sure you remember these formulas for the next video, and yeah, see you in my other videos then.